In this video, we are going to connect to a Solidity smart contract and a Solana program from a Flutter app client to store a number and an address in Polygon, Binance Smart Chain, and Solana using QuickNode RPCs. Our goal is to establish the basics to create a multi-chain Web3 mobile game. We will start cloning the repository from our last tutorial where we created a multi-chain login for our Dino Grow game. Link for the repo is in the description. Create a .env file in the root and create these three variables. We need to go to QuickNode.com and create endpoints for Polygon Mumbai, Binance Testnet, and Solana DevNet, and place them in each variable accordingly. Now let's make the dependencies part of our pubspec file look like this. Adding these 5 new libraries, let's also import this build runner dev dependency. We'll create a models folder, and inside it, a file connectdata.dart. This will help us separate blockchain-related code from the UI code. Let's create this enum chain with the chains we'll be working with for now, and a class connectData with all these variables that we'll use to handle the connection to different blockchains from different pages of our app. Now let's create a services folder, and inside it, a file getConnectData. We'll use these imports, and a global connectData variable. The function connectData will return a connectData instance. We first declare a storage variable and read the chain in mnemonic form, the internal storage. We load the .env file, and depending on the chain we just read, save the appropriate RPC read from the .env file. In our data variable, save the selected chain, and call a function to create the credentials. This function will be the same for any EVM compatible network. For Solana, we'll create a different function. The credentials EVM function will receive the mnemonic stored in the device. Here's a very important part of this tutorial. We'll convert this mnemonic to a seed list using the mnemonic2seed function of the BIP39 library. This list we'll use to instantiate a BIP32 object. We'll call rootSeed. Now we will use this derivation path so that our account will be compatible with the EVM networks. This is also the derivation path used by MetaMask and other major wallets. Our rootSeed object exposes a method-derived path so that we can derive the account we are looking for. In this case, we are deriving the first account of the derivation path, represented in this 0. We'll access the private key parameter in the object returned by the derive path method. This will give us a list representing the private key. But we need to encode this list into an hexadecimal using the hex library, just like you see on screen. And with this hexadecimal private key, we can now obtain our ETH private key instance. We'll call credentials, which we will save in the cred EVM parameters of our connectData object. The credentials Solana function will only use the from mnemonic method available in the ED255HD key pair class of the Solana library to obtain the key pair, which we will store in the appropriate parameter. Our getConnectData function is ready. Now let's also create a display data model for the elements we'll display in the UI. In the models folder, create a display data.dart field, and inside it create this display data class with all these variables. Now let's create the service to obtain this data. In the services folder, create a getDisplayData file. Inside it, we'll expose a function getDisplayData that will receive a connectData instance and will return a displayData instance. In this function, depending on the selected chain present in the connectData object, we will save the appropriate logo, chain name, and address like so. We'll create the truncate address from this truncate string function and save it and return the display data. To obtain the balance for our address, let's create a getBalance file, also in the services folder. Here we'll create 2 functions, balance Solana and balance EVM, both receiving the connect, data, and both will return the balance as a string. For the Solana balance, we create a WS URL version of our RPC and create the Solana client, and get the balance using the client and convert it to SOL format, and return it as a string. All this was explained in our last tutorial. We do a similar process for the EVM compatible networks, creating the client and using it to get the balance of our address, and then convert it to ethers and return it as string. Now back to our display data file, we can now call the balance EVM to save the balance for our EVM chains, and the balance Solana for our Solana case. Now our homepage will be a bit cleaner. We'll have all this imports, and our My Homepage widget will create instances for both connect data and display data classes, and we'll call this read data function in the init state. This function will populate our connect data and display data classes using the services we created. We'll use the very same scaffold we had before with the button to go back, the title, the truncated address, and the logo of the chain with the balance. We'll now add a play button that will lead us to this random route. The idea here is to have a random number that we can save in different smart contracts for the different chains. We'll be creating this contract soon to save this data. For now, let's create a game page, Dart file in the pages folder, and let's create this random number game widget. We can create the random root here in the main.dart file to have it readily available. Let's create these variables, importing the libraries when necessary. And we'll call this startRandom number generator function in the init state. This function will display random integers from 0 to 1000 on screen, while the isFrozen flag remains false. We'll create a scaffold with a title and a button to go back to the home root. In the body, we'll have a column centered and wrapped in a gesture detector, like so. In the column, we'll display the random number, and when the user taps, we'll call this freeze number function if the number is not already frozen. This function will only change the flag to true, and when that happens, an elevate button will show to send the number to the different chains. Now let's create the contracts that will store our random number in the different blockchains. We'll start with the Solidity contract. Go to remix.ethereum.org and create a savescore.sol file in the contracts folder. We'll declare the Solidity version like so, and create the user score contract. Our contract will have a struct user scored that will house a win256 score variable and a user address variable. We'll also declare a mapping to store the scores. This mapping will relate addresses to user score struct, and we'll call it scores. And we'll create the function savescore, which will receive the score and an address. This is the data we're going to send from our app. The function will store in the scores mapping both the score and the address received, and they will be mapped to the address calling the function and signing the transaction. In the compile tab, make sure to select this 0.8.9 compiler and hit compile. When the process is done, we can copy the ABI like so. And back in VS Code, we will create an ABI.json file in the assets folder to paste the ABI we just created. This ABI will have all the information needed to interact with the contract. Now, go to the Deploy tab, and here, let's select Injected Provider in the Environment tab. This will connect the page to our MetaMask. To deploy to BSC testnet, we need to configure our MetaMask. In Add Network, then Add Network manually. We'll give it a name, and look for your BSC testnet QuickNode RPC, and paste it in new RPC URL. Chain ID 97, TBNB for currency symbol, and save. It's important to get tokens for your transaction in any of the chains faucet available online, like testnet.bnbchain.org, faucet, smart for the BSC testnet. We can see how our injected provider now reads custom 97 network, hit deploy, and our contract is ready for interaction in the Binance Smart Chain testnet. We'll repeat the process for the Mumbai testnet. Configure your MetaMask, adding a new network manually. Place your QuickNode, Polygon, Mumbai RPC where it belongs, and 80001 for chain ID, Matic for currency symbol, and save. Check the custom ID for the injected provider and deploy. Our contract is ready in both EVM networks. Now let's create our Solana program. Go to beta.solpg.io and create a new Anchor Rust project called SaveScore. We're going to use our custom QuickNode RPC in the settings to connect to Solana's DevNet. We'll delete everything under the declaration ID. The process for creating this very simple contract in Solana Rust is a bit more complicated, and we have to take into consideration several other things. We have several tutorials in our channel that you can use to get more information on creating Solana programs. Let's define our program SaveScore with this use super instruction. The structure that will hold the data, we'll call it user score, similar to what we just did in Solidity, and it's going to have a U32 score variable and a user pub key variable. Now, we need to create a program-derived account, which will be the account that relates a specific address with the data we are going to save from that address. So we create this struct SaveScore that will hold 3 accounts. The first one we'll call GScore, and is an account holding a user score struct. This account will derive it with the following instructions: init if needed, to create it. The player account will pay for the transaction. The space, consisting of 8 bytes of standard space, plus 5 for the score number, and 32 bytes for the user address. This seed that we design to derive the account, using the random word and the user address, and the bump parameter. The other 2 accounts will be the player account, which will be the signer of the transaction, and the system program, which is the main Solana program account. We'll also create another struct with the same 3 accounts called updateScore. This is because in Solana, if we want to update the data on a PDA or program-derived account, we reallocate the space instead of destroying the already created PDA, which is a more expensive process. The updateScore struct will only differ from the SaveScore struct in the instructions to derive the GScore account. These will be the mutable instruction, this realloc instruction with the same set of bytes for space, the same seed and bump parameters, and this realloc instructions to set up the payer for the reallocation of space and realloc 0 to effectively discard all previous data. Now that we have the accounts needed for our program, let's create the functions which we'll use to write data on the blockchain. The first function, SaveScore, will use only the first time a player saves a score, and thus we need to create the PDA. This function will use the struct SaveScore as context and will receive the U32 number score and the pub key user. Inside it, we'll declare a GScore account taken from the context like so, and we'll save the score number received from the client in its score parameter. We'll display a message with the new score, and lastly we'll save the user address received in the function to the appropriate parameter, and we'll also create the updateScore function, which will be used to rewrite data on the PDA when it has already been created. This function will use the updateScore struct as context and will write the received data to the GScore account accordingly, with the messages displaying the previous and new scores. We are ready to compile our program with the build command and deploy it to Solana DevNet using deploy. Now that we have our contracts ready in all platforms, let's write the functions to send the scores from Flutter. Let's create a SaveScore.dart file in the services folder. We'll use all these libraries, and we'll expose a SaveScore function that will return a string with the hash resulting from the transaction. The function will receive a connect data instance and the score obtained in the game. In this function, we will switch through the selected chains. And in case we're working in the BSC testnet, we'll first define our contract address. This we can obtain in Remix in the Deployed Contracts tab. Make sure to get the one obtained when deploying to Binance Chain. And we'll call a SaveScore EVM function with the RPC, the contract address, the score, and the credentials for the EVM. The function will return a string, and here we'll access our Solidity contract for all EVM chains. First, we load the ABI we have saved in our assets folder. Now we can instantiate the contract with the deployed contract class, sending the ABI as a conter ABI instance, like so, with the ABI read from the assets and the name we gave our contract in Solidity, and the contract address. We must also define the function we will be using from the contract through this function method available for the contract instance. Our function is called SaveScore. Now we create our client just like we did to get the balance before. Let's define this gas price and chained variables like so. And now we'll assemble our transaction using the send transaction method in our client, which receives the EVM credentials, the actual transaction which we'll create next, and the chained. Our transaction receives the contract and the function we just created, and the parameters. In our case, the score and the user address. Remember, these are the parameters that our SaveScore function is expecting in the Solidity contract. Lastly, let's put this from parameter with the user address and the gas price. We'll return the result of the transaction. For the Polygon case, we'll do the same, but making sure we use the appropriate contract address. Now, in the Solana case, we'll call this SaveScore Solana function. This function will also return a string and will receive the RPC, the score to be written on the blockchain, and the credentials for Solana. First thing, we create our Solana client like we did before to get the balance. Now let's define our program address, like so. This address we can get in SOLPG in the declare ID declaration on top of the program's code after it has been deployed. We'll also declare the system program ID like so. Now we need to derive our PDA using the find program address method like so, with the seed we defined in our program. That is, the string random and the user address. We also send the program address like so. Now we need to find out if the PDA has already been created or not. This will determine whether we use the SaveScore method or the UpdateScore method. So we define this string method and initialize it to UpdateScore, and we use our client to get the PDA info and store the result in this result variable. If it comes in null, it means the PDA doesn't exist. So we'll change the method to SaveScore, which does have the instructions to initialize the PDA. Else UpdateScore will be used. Now let's construct an object with the parameters we are going to send to our program functions. We must do this using a Borsch serializable class, so that our program understands the data we are sending. So we'll create an instance of this SaveScore anchor class with the score and the user address. Now to define this class, let's create a file in our models folder called SaveScore anchor, and we'll make it look like this. Note this part import of a SaveScoreG.dart file. This file is going to be automatically created soon using build runner, which recognizes this Borsch serializable tag and performs the operation. Our SaveScore anchor class has the score and user parameters with the necessary Borsch types. We run Flutter pub, run build, runner build, and it creates our complementary file. Now we can import the SaveScore anchor class like so, and we create our instruction with the method for method of the anchor instruction class with the program id, the method variable with the name of the function. And in the arguments, we'll use the SaveScore instance we just created, accessing the toBorsch method that has been automatically added by build runner, converted to list, and with this, we instantiate the byte array class that our forMethod method is expecting. Now, if you remember, our functions in the Solana program will need 3 accounts as context. We must send them in this account parameter. The first one will be our PDA, then the user address and the system program ID. All of them converted to account meta like so. Let's place this namespace parameter global, and now let's create a Solana message with our instruction. And we send the transaction with the client's method, send and confirm transaction with the message and the credentials in the signer's parameters, and we'll return the result of the transaction. Let's go back to our game page and send our random number using our function SaveScore. First, let's get the data for our connect data and display data objects using the relevant function, importing the respective libraries like so. And we can now call our SaveScore function with the random number converted to big int and also the connect data. Let's call this display result function to show an alert dialog with the transaction hash. So we'll have an alert dialog with a close button to go back to the home route. and in the content, we'll display the logo of the chain we're currently connected to, and the transaction hash with an icon to copy it to the clipboard. We can run our app, and upon logging in and connecting to Polygon, we hit play, stop the number generator, and send it to the contract. We'll soon have our result on screen, which we can look up in the Mumbai Polygon scan. And we see the transaction that has used the SaveScore function. We can do the same in the Binance Smart Chain. And in Solana, we also have success. We can verify this Solana transaction in Solana FM, connect to DevNet, and in the button we can see the logs showing the score we obtained. We hope this video is helping you build your own Web3 game. Subscribe, like, comment, and share. See you next time.